Okay, good morning, folks. This is the end of the end of week 6. All right. Now we're going to start a topic today, and it's going to be it. This is not going to be discussed anymore, and there's a homework that is associated with it, and it's already posted, and the solution of it is also posted on YouTube. Ordinarily, homework like this would be due next week, 24 hours after the end of your lab next week. However, next week is a summer break. Therefore, your homework is due June 30th at 12 noon. That means I think it's 3 days after you return from your summer break. So there's plenty of time, and there's going to be a firm deadline at 12 p.m. Wednesday afternoon, June 30th. It's going to be cut off for submission. Now, uh, this one homework that I'm going to ask you to do, the last one on this business of finite elements, which we just talked about, this does not require any PDF file. Okay? So all you have to do is to submit your CATIA part file and the analysis file. That's it. Don't worry about the PDFs. Okay. All right. So what is this about? So first of all, are there any questions before we start the topic? Okay. If there are no questions, we move on. So the topic that we want to discuss is the idea of buckling. Now, you don't want to be present under structure that buckled. Okay. Here are some examples. This is a reinforced concrete fat column. See the reinforcement here, which has buckle. This is just a buckled steel column. Could be I-beam or something along that line. Here's a water tower. This left piece buckled, and of course that goes with it. Okay. Now, there are two things that you really want to stay away when it comes to failure. Plastic, the idea of yielding and things like that is not really that worrisome. For example, if you're standing under, for example, an I-beam, and that I-beam you put too much load on it, so that, for example, it kind of sags too much, and then you look at it, you hope that nobody puts more weight on it. You don't have to run away, pretty much. But if you're standing, for example, under or I don't know, hanging on to an I-beam that is axially loaded in compression, and there reaches a point where suddenly this thing completely buckles, and you're in trouble. Okay, there's no way to run away, pretty much. The other mode of failure that's very dangerous is the fatigue failure. In other words, you don't see anything happening until suddenly the thing snaps into two pieces. Okay, so fatigue and buckling are one or two of the most dangerous modes of failure. Whereas yielding, we can still live with it and hope that things will work out. Now, the first time you saw this thing was in I think Dr. Green's class, which was under buckling of beams. There is a very well-known work by Euler, which says that if you have a beam, let's not worry about how it's supported. It could be simply supported at both ends, such as this. This is simply supported at both ends, pin, or it can be a clamp and a pin, or actually free, or it can be a clamp and a pin, etc. Let's not worry about these. They all give you a critical load, and this is under compression. They all give you a critical load, which is called a Euler buckling load, which comes from this formula. Now remember, this works only for columns. If you have something else, then of course you can't use this, unless you approximate it with a column. But anyway, look at what's involved here. Of course, pi is pi. E is Young's modulus of the material. I is the cross-sectional moment of inertia of the beam, divided by L. L is the length, big L is the length of the beam. However, depending on how the supports are, you put a multiplier here. For example, if it's simply supported like that, pin and pin, your K is 1. On the other hand, if it's clamped, your K is 0.5. And this KL is called the effective length. Okay, so these you have seen in your stress analysis course. Now, of course, you guys, yeah, you took it last year. That's right, last fall. Now, this formula is fine, but it is what is called a non-conservative formula. That means that in real life, the buckling load is in all likelihood well below this number. Okay, so yeah, sure, calculate your P, but don't think that unless P gets to that value, the structure will buckle. P will buckle below that. It's still a good piece of information. It's good a piece of information. Yeah, you don't have to worry about beyond that, but it doesn't mean in real life you get this far and then you're in trouble. It was well below this. Now, a couple of things here. This can also be plotted in a way, so I'm going to go here and show you what the plot looks like. This formula that I gave you is valid only if material does not yield. If the material is yield, obviously this is nonsense. This is nonsense if the material yields. So what happens, what you do is you plot that guy, you plot this guy, but there's a cutoff here, and this is not, it's not P, it's P over area, okay? It's called yield, well, the yield strength. So this Euler buckling formula is valid only in here, in this range of, in this range of load, or in this range of length. Think about it. It's actually called slenderest ratio. It's not quite L. It's the ratio of L over something. Okay, so it's right there. Okay, now what this tells you is that if your structure is fat and short, that means the slenderest ratio is actually very small. Okay, and the material, like here, for example, fat and short, okay, slenderest ratio below this, the material actually yields before it buckles, such as, I mean, this buckled, but what I'm saying is that if it was a big fat piece of steel, this will not happen. Maybe if it was shorter, whatever. But if the material is slender, or the beam is slender, very tall and thin, think about it like that, okay? It really has nothing to do with the length and its height and its cross section. Is the ratio of two things, okay? But anyway, if the material is, if the part is very slender, notice that it buckles at lower load, much lower load, okay? This is a stress, but still you can multiply it by A, you get your load. So yeah, so this is be careful. Now, so there is the opportunity of people predicting this critical load for structures which are not beam, and you know, they're structured, they're frames maybe, they're three-dimensional things which are in space, you know, and or you know, a pressure vessel, for example, buckling under compressive load, or a pop can that you can stop on it, you can step on it, and then after, if you press hard enough, it just buckles. You have experienced that, I'm sure. Or put it with your, or buckle it with your forehead. I'm sure you have done many things like that. Yeah, it need not be may not have been the pop can though. Anyways, these formulas are no good anymore. You have to do with the finite element. So today I'm going to show you, and it's very easy. The only thing you've got to watch out is this business of, he'll tell you, but that's not real life. May not be real life. In all likelihood, it is not real life. Okay. So today I'm going to do this problem for you. It's a variation of that. Okay, so it's almost the same problem, but I've made some changes because I'm doing it in several different pieces. Now, if you think about it, first of all, what the heck is this? Okay, well, obviously you can recognize it. This is, think about it, because I put I, obviously the intention was here to show you that this is a beam, okay, or a column, think about it like that. This is on a roller, this is on a roller, and you compress this thing with a load P. Now, I drew it like this, but you can also visualize it a different way. So I'm going to go down here and show you something. It could be this. In other words, if you have a square-like object like this, and you compress it in all directions at the corners at 45 degrees, when you think about it, this is a plane of symmetry, this is a plane of symmetry, and when you took 1/4 of that, 1/4 of that, because this is a plane of symmetry, it can go only up and down, roller. Because this is a plane of symmetry, it can go only sideways, roller. So roller, roller, P, which is exactly what I've drawn here. So when it comes to modeling this problem, although it looks kind of weird, but it's basically a structure like that you're applying a load and you're trying to buckle it. Now, there's a couple of things you have to worry about, and that is when you're doing buckling calculations, you're at your own risk if you took planes of symmetry into account. And I'll show you why. Because this structure, when you load it like that, when you load it like this, it will buckle, but not necessarily in this mode. It will buckle out of plane first. And that may or may not be of interest to you. If it's of interest to you and you made the assumption that this is plane of symmetry are applied, for example, or it does not go out of the plane, obviously that's wrong. The same thing is we calculate natural frequencies. You suppress modes for frequency, for vibration, which is not what we're doing here, or for buckling. So if you're using planes of symmetry in buckling to reduce your model, be aware of the fact that what you get is what you pay for. In other words, for that mode of deformation, you get a non-conservative buckling load. But this can also buckle well below that load out of plane, or when symmetry is not taken into consideration. This is why, time permitting, when we come to this problem, I'll do this problem for you 3 different ways. The full structure, like this. This is a full structure. That's the object that you have in your hand and you're compressing on all sides. Then I will assume that I've done only half of that. Half meaning the thickness is half. So I can do that, but be aware of the fact that you're suppressing some buckling load. You'll see that the lowest buckling load may be not the one that this produces. And then you can even do worse. You can take 2 more planes of symmetry and take this. Okay? So and this is the one that's not in the book, by the way. All right. Are there any questions? Okay. So my dimensions are like this. I'm going to do a few things that you may or may not like. I don't know. So I'm going to do this in a very weird way. The nominal size is 10 by 10, 10 inch by 10 inch nominal. And then the thickness is 0.5 up, 0.5 down. Okay? That's it. So when you think about it, this outside, uh, yeah. So let me show you what dimension I'm going to be choosing. First of all, part. Immediately save. desktop, new folder. And this one, I'm going to say buckling. Okay, no problem. Buckling. Stop 51. Okay. And that part, I'm going to say save as no planes of symmetry. No planes of symmetry. Okay. Make it. So on this plane, I will sketch the rectangle, square actually, of size 10.5 by 10.5. So this is 10.5. And this is 10.5. Good. And then inside, I'm going to draw one 9.5, 9.5, and 9.5. The different ways of making this part, I leave it to you to decide. This is how I'm doing it right now. I did it differently when I was preparing the lecture, but this is fine. 9.5. I'm hoping the distance between this and this is 1, so let's measure it. Distance between this and this better be 1. Oh, sorry. So these are not right. This should be 11. The other one should be 9. 11. Yeah. This should be 9. 11. This one should be 9. And this should be 11. Whoa, longer than I thought. Okay, now like 0.5 in each direction. 0.5 in each direction, so it's going to be mirror extent. 0.5. There. So this is that. Okay, good. Let's make it out of steel. Oh, you know what I want to do? I would like to create a coordinate system because remember, I want to load this thing at 45-degree angle in both directions. That being the case, I'm going to create a coordinate system. This is no good because this looks like the original one, right? The original one means global. So I'm going to rotate, put the cursor there, rotate the x-axis by 45 degrees. And watch what happens to that red thingy in the middle. It turns, and now it's at 45 degrees. So when I say apply a load in the direction y, it's actually going to be direction at 45 degrees. Okay, good. So we made that thing. Did we apply materials? Apply material here. Metal, I think that particular chapter uses aluminum, but that will use the same thing. And save. Okay, done. So now we're going to go to generative structure analysis. By the way, this problem can be done with beams, can be done with shells. I'm using solids, okay? This problem can be done with any one of those three. And I'm going to change the size. I'll make it a little bit smaller, 0.2, something like that. Maybe 0.2. That's too small. Make it 0.4, linear. Okay. So you can look at your mesh, right-click, mesh visualization. There we are. Okay. Deactivate the mesh. Very good. Now, we're going to apply loads. Okay, load. There, force, right there, force. On that edge. In the direction negative y. Negative y, like that. Negative y. User coordinate system, see that? User, ordinarily it's global. Let me put here global. I don't want global. I want user. I created this because I want to use it. So global, or not global, user, and it's waiting you to go and pick it. So here we are. In the direction y, I put a dummy load of 1. Dummy load, because what CATIA will give you is the buckling factor. So if you take that number and you multiply it by the dummy load that you put in there, you get your buckling load. Okay, so I put 1 because I'm lazy. I don't want to put 3.5 thousand and then multiply it by the buckling factor. I'll put a 1, whatever buckling factor I have, I multiply it by 1. Okay, and look at what happens, by the way. If you zoom in, you see what happens. Because you're using that coordinate system, it's applying it like so, and then okay, and then do it again for the other edge. This edge diametrically opposed. The only difference, this number is not negative, it's positive, and the coordinate system you still have to pick like that. Say okay, look, it's compressing it. This coordinate system is very useful in general because your loads are not always along the x and y, the regular x and y. Okay, let's do it on the side, on this edge. Now notice that this edge is compressing it in the z direction, local z direction. So let's take this thing out. Let's put a -1 here. And it's expecting you to select the coordinate system right there. You see this? You see that? It's compressing it. And do it again on this side, except that the sign is going to be positive. Coordinate system is still there. Right there. And it's compressive exactly like the way I want it. Compressed on this side, compressed on that side. Now, by the way, let's go ahead and save our analysis file, save management, analysis, save as. This is the right folder. The only thing I want to do at the beginning of this, I would like to say, no planes of symmetry. Okay. Good. There's only, I don't know, 14, 15 people here, including me and GA. There's only 13 students. I'm just cautioning you, and the people you're not here. Of course, you guys are here, so you can hear me. On the test, the files must be named properly. Your student ID number, your last name, and then the rest of the identifier. Buckling problem, no planes of symmetry, blah, blah, blah. Please. And I've prepared a video, put it up there for people to watch. Okay, good. Let's move on. Now, this is a static problem. This is a static problem. I can run it. It has nothing to do with buckling right now. All I did was to apply loads here and there. This is a static problem and I can run it. The only problem is that this could have been sitting in the back of a truck and the truck was moving and you were compressing both sides like that. So the actual displacement of points when it buckles is not known because the truck is moving. Anything that you have in the back of the truck, you add to it the displacement of the truck or a rocket moving in space. So this, when I run it, it will bomb out. We know that. Okay? If this was a static problem, and this is all you were told, forget about buckling, that is not going to work. You'll see. So I have to fix it Fix it meaning put some restraints on it that does not give you artificial stresses, but at least it will be statically in equilibrium. And there we are. And you can see that you animate it. This is all moving as a rigid body. We're not surprised. We have done things like this. Okay? So there is an easy way of doing it, but I'm not going to tell you that. Nobody asked, so I'm not going to bother. But I did it a different way for you and using the 1, 2, 3 rule. The 1, 2, 3 rule is, look, I don't want this thing to move as a rigid body when I'm sitting in the back of the truck. Basically, I want this thing to sit stationary with respect to the back of the truck. So here is the way it works. 1, 2, 3 rule, and it's not arbitrary, you know, just take one point, say, don't go in direction 1, 2, 3. So this point is now fixed. It will not go with the truck. Think about it like that. It's actually going with the truck. With respect to the truck is fixed. Okay? Another corner point, I'm not going to let it move in the upward direction and direction X. I will let it move in the direction Y, because if I fixed it in the direction Y, this is fixed, well, obviously this length is not going to change. Finally, a third one, I'm not going to come out of the plane. That means do not move in direction X. So now with respect to the back of the truck where this guy is moving, you are moving with it and you're compressing this thing. This is staying stationary. And if necessary, we go fix it. But I'm pretty sure this is going to work. I hope. No problem. So when you compress it, how does it look like? Let me change the scale. Yeah, you don't have to be a genius to see this. You're compressing it. This has nothing to do with buckling. This thing kind of shrinks in all directions like that. Can you see that? This has nothing to do with buckling, because you didn't say buckling. You said apply static load, and that's what it did. Now we're going to close this. And now we're going to go and insert buckling. In CATIA, first you have to do a static analysis. You must do that first. And then you're going to insert a buckling case. And notice that when you do that, it says, oh, where is that static case that you did? Where is that static solution that you did? Now I can go and pick it from the tree because I did it. You see that? It's expecting, it's asking you, where is the reference static case? It's right there, the one that I just did. You select it and you say, okay, and that's it, run. And it's finished. Now we want to look at deformation. Click on this. Look at that. Your first load is out of plane, not in plane. This object, if you compress that from both sides, at least linear buckling analysis predicts that it will first buckle out of plane. It's a lot easier to make it like this. Now, let me close that. Double click on this. And then there is the occurrence tab. We never had to worry about this thing. And it shows you the buckling factor and multiplied by 1. Remember the one that you applied, that P that you applied? You're going to get the different buckling loads. For example, this mode will buckle at 1, whatever, that unit was 1 pound, right? 1 pound times this at almost 24,000 pounds, and it will buckle like that. You might say, whoa, my God, 24,000 pounds. That's impossible because 24,000 pounds is a gigantic load. That's because, remember, this is a non-conservative estimate. It says, don't worry about anything more than 24,000 pounds. But the real life is going to make this thing buckle at that mode, for example, well below 24,000 pounds. If this was very slender, these become more meaningful. If this is fat, and it is fat, then You remember I showed you that plot. You got to be very careful. Now, here's the other buckling mode. The next one. The next one. Like that. If you look at the view from, this is actually, if you look at the view from the front, maybe you can see it better. Ah, that is this load. Still in plane. This is in plane, but it's this load. It is not, where is that? It is not this that I want in the book. Okay, so we'll get there in a second. All right, cancel, double click, take the next one. I don't know. This is also out of plane. You can see that. Look at the side. It curved. This is out of plane. Double click. That guy. Now this is in plane, and if you go to the front view, that's what I want. When I say that's what I want, is what is done in the book for you. See that this is in plane, and that piece goes up, this piece goes in, and this is in plane. So you get a lot of junk here, but some of these are out of plane, some of these are in plane. All of these are totally nonsense. In general, these are non-conservative. Things will buckle well below this, particularly if it's fats. Slenderness ratio is very, very small, okay? So the one that we want, or at least done in the book, is something like that. This is in plane. If you look at the view from the side, very little goes out. Oh, no, that one's, where is this? Not this one, not this one. Oh, maybe it was that one, yeah. So this seems to be in plane. You look at the view from the front. Oh, no. Well, let's look at the view from the side here. Yeah, this is also a little bit bent out, so let's see this. What is the front view of this? No, this is, you see this? There's more to it than what I wanted. Okay, so anyway, this was with no planes of symmetry. So what I'm going to do now is kill this, and then I'm going to say, okay, file, say management, save as the part. I'm going to save it as 3 planes of symmetry. 3 planes of symmetry. 3 planes of symmetry. Because I don't want to destroy this. I'm going to give it a different name so that when I changed it, the original part will not be changed. Now I'm going to, first of all, instead of padding it, I could have padded by 0.5. It would have given me 1. But since I'm in the cutting mode, splitting mode, let's do that. Okay. Split it with the YZ. It just reduces this by half. There, you can see that. I could have padded it 0.5 instead of. Split it with XZ. No, we already did XZ. YZ. No. XZ. Yeah, okay, XZ. There. Split it with XY. Okay, good. I didn't destroy my original part because I renamed this thing on a different name. You can see that. 3 planes of symmetry. And all I do is you click on the floppy and it'll do it for you. Okay? Save it. Now we're going to do the analysis. Generative structure analysis. CATIA sees a 3-dimensional object. Okay? And let's put the restraints in there. Back face, surface slider. Bottom face, surface slider. You can do it all at the same time, by the way. Let's do it all at the same time. Surface slider here, surface slider there. By doing this, you're saying, I don't care about the loads that may buckle this thing out of plane. Just give me the in-plane ones. Okay? That may or may not be okay. If you know what you're doing, maybe okay. If not, you're in trouble. Because you're going to ignore those buckling loads, which may be lower than what you get here. And then when you fully load the structure, it will buckle out of plane at a much lower load than what this guy told you. Okay, now we do exactly the same thing as before. In other words, we apply a force right up there. User, there is my user coordinate system. The direction is along y, and it's -1. So it's not this guy, it is this, -1. And you can see, you see, right there. Okay. Now, when I run this thing, it's not going to bomb out, because last time it bombed out because it was free to move as a rigid body. It cannot move in the direction X because you put surface slider in the back. It cannot move in the direction Y, global Y, because you put a surface slider on the side. And will not move in the direction Z as a rigid body because you put a surface slider at the bottom. So I don't have to worry about it. It's going to run. Last time I had to go and apply that 1, 2, 3 ruly, you know. This one will run. But it's a static solution. What do you expect? You look at the deformation, it's just going to go inward. That's it. Yeah, you can animate it. This is not buckling. It says if it doesn't buckle, it's going to move like this, which we know. Okay, good. Now you're going to say insert buckling case. It says, where is that static solution that you did? Well, it's right here. And you say, okay. And you're going to run it. You don't have to do anything else. And it's going to be done. There. Now let's look at the deformation. Okay. You see, this is in plane. If you look at the view from the side, it will not go out of plane. That doesn't surprise you because you put surface slider here. Okay. And of course, the other ones also will not go because you put surface sliders on the side. It'll go up and down, it'll go sideways. So yeah, you can get your buckling loads here. However, you ignored other buckling loads which are lower than this, out of plane one. So if you double click on that and select the occurrence tab, and there we are. Okay. So to get this mode, you need to apply, here's what happens. You need to apply this thing by dummy force of 1. So it's that much, okay? However, that is only for the side that is facing you. There is also a back side that you did not model. So you're going to have to multiply this thing by 2. Because this will only give you the buckling load for the front piece that you model. Remember, you split that thing into 2 halves. You didn't do the back one. So you have to multiply this thing by 2. You got to be careful to buckle this structure. In other words, surface slider, surface slider, surface slider. This is what you need. But if this was part of the bigger structure that you did not model because of because you didn't model 3D, you need to multiply this thing by 2. Yeah. Okay. Are there any questions? Now the problem that I have for the homework for you, where is that homework? The homework that was uploaded for you on Blackboard and YouTube, solution on YouTube. It says, okay, this is due Wednesday, June 30th. So you go have a good time, your summer vacation, 12 p.m. Come back on the 28th, submit this thing by the 30th. We don't need a PDF file, okay? Submit problem 1 only. This is you guys, lab 51. Problem 1 only. Problem 1 is a cylindrical shell like that. The bottom of it is clamped, and you're applying a pressure compressive load to that edge. See that? To that edge. And you are asked to use parabolic shell elements to model this. Use this size, parabolic. Now, the people in lab 54, not 54, 52, are asked to submit problem 2. You're asked to submit problem 1. They're asked to submit problem 2. The only difference between problem 1 and problem 2 is that here you're asked to model it as solid elements. Okay, you can see that these are solid now. There's the depth. In your case, these are shell elements. There is no depth. The shell thickness you specify by 2D property, but here you just model that thing and then thicken it. You can take your own model, which was a shell surface, and thicken it, not thicken it, thicken it by 0.5 outward, 0.5 inward, because this has total thickness of 1. 0.5 out, 0.5 in from the surface, and you get this object, and you mesh this object, and use, again, parabolic elements with 2 as the size.